Everyone. Let us start our program with an audio clip which will be playing from YouTube.
The thing is that there can be in mathematics, particularly in number theory, there can be theorems about numbers that are tremendously hard to prove. And maybe when you prove them, you don't feel you've got any insight as to why they're true. I mean, in fact, asking why, although I keep on asking why, I don't understand what it means to ask why. And I don't understand what would count as an answer to that question.
That's the voice of John Horton.
That was the voice of Professor John Horton Conway, a legendary mathematician who stood out for his love of games and for bringing mathematics to the masses. And we lost the legacy of this math luminary last year on April 11, 2020 because of complications related to COVID-19. And last Saturday, as a small tribute to this reason, we started a lecture series, tribute to John Conway, a lecture series on the memory of Professor Conway. I want to thank you all for participating in our first program where we remembered Conway through interaction with his doctoral student, Professor Robert Wilson, who is also an eminent group theorist. Today is the second day of this lecture series where we will be having two sessions. First session is the mathematical artist of play, a tribute to Conway by Professor R. Ramanujam, followed by notes about the game of life and some lifelike rules by Professor Genova Martinez. So let me first formally introduce our first speaker, Professor R. Ramanujam, an eminent scientist, mathematician, and activist. Professor R. Ramanujam, bluntly known as Jam, which all of us call him, is a professor in the Theoretical Computer Science Research Group in the Institute of Mathematical Sciences, Chennai, India. His research interests are mathematical and philosophical logic in computer science and theory of computation, and their applications to theory of distributed systems, game theory, and security theory. His other research interests include temporal logic and verification, partial order models of concurrency, and logics of knowledge. He is on the editorial board of ACM Transactions and Computational Logic. He was Lawrence Fellow of the Royal Netherlands Academy of Sciences, and he has been actively involved in the Indian Association for Research in Computing Sciences and Association for Logic in India. Apart from this academics, he is also associated with the Tamil Nadu Science Forum since 1990s, active in its involvement in science popularization and school education. He is also editor of Cellular, a monthly science magazine for children. He was a member of the Yashpal committee that formulated the National Curriculum Framework 2005, and he is Vice President of the Mathematics Teacher Association of India, a member of Core Committee of CS Pathshala and Asian India Initiative. Last year, as an obituary, Jam has written an article about Conway's work of the same title as our talk, which we recently came to know. That is obviously from the 40s hours. So naturally, after knowing that, we approached him to talk implications and dimensions of Conway's work, which are almost totally gray zones to many of us who knew nothing about Conway except the game of life. So finally, here he is. Now it's over to you, Jam. We are excitedly and eagerly waiting to listen to you.
Thank you. Thank you, Kamarika. Okay, I will present my screen. Just one moment. Are you able to see the screen?
Yeah.
Very good. And, the audio is okay? Are you able to hear me?
Yes, sir.
Okay. Fine. So, thank you very much. Uh, yeah, it's a pleasure for me to talk in this forum. I mean, these are all very dear friends. And after listening to Professor Robert Wilson last week, I don't know whether I should be talking here. There are so many Conway experts speaking in this series. I'm not an expert, but well, if there was a Conway fan club, I would certainly be a member. Right? That's all my qualifications. So thanks very much for the invitation to speak, and do feel free to interrupt and talk at any time. Uh, yeah, as Kamalika mentioned, last year when Conway passed away, I wrote an article at Right Angles, Tulare, a couple of other occasions where I could talk to children and school teachers about Conway. So the content of the talk is pretty much there, what is there in the article. So for some of the people who may have read the article, they may not be new. But the other thing is that since there is, there's a lot of interest on game of life and cellular automata, and there are other talks on that, I'm not going to talk about the game of life. I thought I would talk about other things about Conway. So in particular, uh, combinatorial game theory, which I didn't see as one of the topics in the tribute series. So I think I will talk more about that. Uh, so let me begin with a personal anecdote. This is, it was in 1996, many years ago now. I was in Rutgers University, spending a month there, in fact, in New Brunswick campus in New Jersey, in the USA. And there was a workshop happening, in fact, partial order methods of verification in Princeton, and I was participating in that workshop. And I had to go to the workshop, and I was staying in Rutgers. So I was standing around in one of the bus stops, waiting for a bus. This was on Sunday morning, and I was standing and reading something and waiting for a bus. Nothing was happening, no bus was coming. And I kept on reading, waiting for a bus, no bus was coming. To get out of the Rutgers campus. And I could see that people passing by were kind of slowing down and looking at me, but it's like, and then suddenly one car stopped. Somebody rolled down the window and asked, "Hey, are you waiting for a bus?" I said, "Yes." "Well, no service on Sundays." I said, "Oh, yeah." So I didn't realize that there were no buses running on Sunday. Previous day, I had taken the bus happily, so I hadn't considered. Well, sure enough, it did say somewhere in the bus stand that there was no service on Sundays. And anyway, so this gentleman looked at me and said, "Well, can I drop you somewhere? Why don't you just hop on?" It was great. So I got in, and I said, "I'll just, if you can drop me at the railway station. This is just outside the Rutgers campus, New Brunswick railway station. Uh, that would be great." He said, "Okay, I'll do that, but where are you going to go?" I said, "Well, I was going to take a train to Princeton Junction." And he said, "Oh, Princeton, are you going to the university?" I said, "Yeah, that's where I'm going." And he said, "Oh, you're in luck. That's where I'm going too. So I'll give you a ride." So that was great. So, and then just as we were turning, he turns around and says, "I'm John Conway." And well, that was the encounter. And so it was a tremendous pleasure for me. I mean, I was completely stunned. I mean, that to encounter John Conway like that. And, it was a wonderful, about a 45-minute ride, and all he talked about was problems. And once I was introduced to him, and that he learned that I was in theoretical computer science. He started talking about graph theory, some problems, and I was telling him about these partial order methods, sort of stuff that we were working on at that time. So he started talking about partial orders. It was a lot of fun. And he dropped me at the workshop in Princeton, and then told me about the lectures, a couple of lectures he was giving during that week. And so I had you know, opportunity during the. In fact, I bunked the next day's workshop to attend Conway's lecture in Princeton. And so, yeah, that was just a personal anecdote, and a very warm and uh, very interesting personality, completely open, and uh, he would. I mean, I've since read a lot about Conway and his life, and talked to other people who have worked with him, and a personality as a personality, quite amazing. He was always willing to interact with anyone as long as if there was some mathematical content. And you just had to approach him with some problems, and it's always interesting. So here is a quotation, that quote that I like very much from Stephen Miller in one of the tributes when Conway passed away last year. And he says, people said he was the only mathematician who could do things with his own bare hands. Um, what he's talking about is this fact that Conway always liked to start from first principles, with very few concepts, and actually build mathematical edifices. And he was very good at that. Uh, so unlike mathematicians who like to work on very deep theorems, right? Conway worked on many things where the definition depth is very low. In the sense that to understand the question, it doesn't need a great deal of many mathematicians call this elementary techniques, and but here elementary is not to mean easy. It means techniques where, unlike for instance, if you're talking about algebraic geometry or something, where you're talking about motives or sheaf theory or something, where to even understand the definitions takes a few years of preparation. Conway always liked to, jump in and look at things. This is something that Robert Wilson talked about last week, how he insisted on looking at some things in a very, very simple manner and build stuff completely on the go. This was an amazing characteristic of Conway. Uh, Here he is, you can see his, in fact, the lecture that I attended in Princeton, the first one that I attended, he walked in with something like this, a bunch of magnetic rods put together in some particular fashion. And he just put it in front of the audience, the gallery, asked questions about it. And, that's, one such object was the beginning of the talk. And the whole object, the lecture was about the construction of a mathematical object. And but in the process, there was so much combinatorics, probability, number theory, so many things that came in. And again, this was very much the spirit of Conway. And so he was famous for, he used to love to play games, including, and when I say games, I mean real games, children's games. And he would go around during summer attending math camps for children, school children, uh, discuss problems with them, pose and solve puzzles. He would carry decks of cards, dice, ropes, coins, coat hangers, sometimes a slinky, even a miniature toy bicycle, take it apart, put it together, all sorts of things. And almost all these things were fodder for his mathematical imagination and for discussions. So that was a great thing about Conway. Now, he was one of the founders of combinatorial game theory. Now, now we are talking about not only playing games, but reasoning about games and thinking about games as mathematical objects. And but then starting with real games that people play. And this is very important for Conway. He actually devised many games, and so that there is this game called football that he was very much into. That other probably Wilson, I don't remember now. Yeah, and in combinatorial game theory, typically you talk about two-player games, turn-based games, players taking turns of perfect information, so it's not like cards. Everything is about board, and often bipartisan games where the set of choices available to both players is identical. So we'll see one such game, and the this is what leads to what is called the Sprague-Grundy theory, and the sort of kind of games that Conway built a lot. So here is a NIM game, and there is this film called Last Year at Marienbad, Alan Rene, remarkable film, where I don't know if anybody has seen it, but that and Rules of the Game by Renoir. These are great French films that I would recommend to anybody. So in this film, there is a character called M. That's all his name is. He carries a bunch of cards, and he's always trying to persuade somebody else to play the game. Now, cards are arranged in rows of one card, three cards, five cards, seven cards. And the idea is that you take turns. So what you do is, when it's your turn, you pick any row. Let's say you look at the row with five cards, right? And you can remove any number of cards. You can remove all five cards, only one card, two cards, three cards, one. And then it's my turn, I play. So you keep doing this, and the one who takes the last card loses. Because after that, uh, now M is always polite. Let's the other person start, and the other person always loses. This is the NIM game. Now, NIM is from the German word Niemann, and it was analyzed in 1904 by Bouton of Harvard University. So this is how the game goes. Two players, one and two, move alternately. And instead of cards, let's just look at piles of counters. There's no ordering, right? There are m piles of counters. And what does a player do? When she moves, she picks a pile and removes non-zero many counters. You can't say I'm passing. No, you can't do that. You have to remove some number of counters from that pile. And when a player cannot move, he loses. And the other person wins. So it's a very simple win-lose game uh, of two players, perfect information, turn-based. Now, how would you play in a game like that? In this, now, of course, games should be played, and but unfortunately, with this online thing, it's a bit of a pain doing all this. I'm not going to play the game with you, but I hope it's easy to think of how it goes. But mathematically, how do you represent the game? Well, every game has three main ingredients. For us, there are two players. In general, there will be n players. Now, what do the rules of the games tell you? The rules of the game specify at any game position whose turn it is to move. We said player one starts and then player two responds, then player one, then player two, like that. And at each time, what are all the moves that are applicable? For instance, there are five piles. You can pick one of the piles. That's a choice you have. And after that, in that pile, if there are ki counters, you remove some non-zero number. And that results in a new game position. Keep doing this, and then there are outcomes or winning conditions that specify at which positions the game is over. And perhaps, depending on the course of play, the outcome of this position. Now, we talk about a win-lose game. So, now, how do you represent the game like this? The most natural representation you can think of it as a tree, right? You can think of it as a tree. Uh, the nodes of the tree are game positions, and when a player makes a move, that is the edge relation on the tree. Right? The root is the initial game position, and the branching degree tells you first player one's choice of moves. Each of them results in a new position, and then at each node, player two's moves gives you the branches. You keep going down. And now notice that since you are forced to remove a non-zero number of counters at every point, and you started with m piles, each having k1, k2, km counters, along every path, the number is going to decrease, and at some point you go to hit a leaf node. And the leaf node you can decorate with who wins, whether it's player one or player two, depending on whose turn it's last. So a finite tree completely describes the moves of the game. Is this clear? This is the idea. So every such game you can represent as a finite tree, and it's typically a finitely branching tree because there are only finitely many moves possible at a time. And every tree node, non-leaf node, is labeled with player 1 or player 2 because one of them is making a move. And every leaf node is annotated with who wins, the outcomes of the game. Now, once you have tree representation like this, there is a theorem by Zermelo, whose centenary is already over, 1913, says that in every finite extensive game or perfect information, you can compute player I whether player I can win or not. Right? It's fairly simple, right? Because backward induction, what does it say? Well, you already know at leaf nodes who wins, right? Now look at a node which is just above a leaf node, right? Uh, take any non-leaf node whose all children are all leaf nodes, right? Take that non-leaf node. Suppose it's player one's turn to move, right? Now, if any one of the children, right, is winning for player one can choose that particular range and win, right? If all the children of that node are nodes where player two wins, no matter what player one does, player two is winning. Right? So what I can do is to decide this non-leaf node as a win for either player one or player two. That's it. Inductively, when you pick any non-leaf node, all the children of the node have been labeled, and therefore this particular node. Keep going up the route, you will find whether it's player one or player two. You are against. So backward induction shows who wins, gives a winning strategy in the case of each game. Forget the fact that it also gives snapshots of it. Now, it is a finite tree, and therefore you can backward induction applies. So, right? So this is a, it's a fantastic thing because you have an algorithm to compute the winning strategy, and the algorithm is linear time because you just have to visit the nodes of the tree. Of course, the tree is huge, but what better can you want? So backward induction completely solves all finite extensive form games of perfect information. So we may as well go home. So the NIM game is completely solved, isn't it? Now, this is the point. If you're only interested in existence of winning strategies, this suffices. But if I also want to look at the structure and strategies, I mean, this way of solving the game leaves you completely unsatisfied. And in fact, in the case of NIM, you just do some combinatorial analysis, you find that there is so much. And what do you do? Now consider the game. Let's say 1, 1, 2. That means here is a heap which has only one counter, another heap with one counter, third heap with two counters. Your turn to move. What will you do? Anyone wants to say? There are three counters in front of you. One counter, two counters. Your turn to play. What will you do?
Any choice would lead me to lose only.
Yeah, what would you do? Sorry, Kamalika.
Yeah, if I take two,
Yeah,
then he will be taking say one, and then
yeah.
the last card will be taken by me. So I'll be
And then
losing.
you lose. Yeah, okay. So suppose that's what happens if you remove all the two. Suppose you remove only one from that. What will happen?
Okay. In that case, oh,
Now
in
you are
if
left
I
with 1, 1, 1. Yeah.
hmm.
Which it's
So
my turn
again,
to move.
hmm.
Then I am faced with 1, 1, 1. I
Hmm.
have to remove one of them, which
Hmm.
means you will be left with 1, 1. If you remove any one of them, yeah, I
Then
am left with 1. So I am the last person. So, okay. So basically, it is easy to see that removing only one from the heap of two counters is not a good idea. Right? So, but removing all counters from that heap works. Yeah. So we can call 1, 1, 2 a winning position for whoever plays, and 1, 1 a losing position for whoever plays, right? If you are faced with 1-1, no matter what you do, you are dead, right? So 1-1 is a losing position. 1-1-2 is a winning position. We don't have to, it's a bipartisan game. Both players have exactly the same set of moves available at any point of time. So we don't have to worry about whose turn it is to move. We can simply label positions as winning positions or losing positions to whoever is moving, right? Okay, you can go further. Is this idea clear? And we can see that 1-1-1 is a winning position. We just saw that, right? If Samalika is faced with 1-1-1, she removes one of them. I am faced with 1-1, which I know is a losing position. And therefore, 1-1-1 is a winning position. So 1-1-1 is a winning position. 1-1-2 is a winning position. Well, now what about a k tuple? Supposing I give you a k tuple of 1s, is it easy to see that it's a winning position if and only if k is odd, right? I mean, the fact that 1-1-1 is a winning position and 1-1 is a losing position. The same argument, in fact, applies for any tuple of ones, which is where the number of ones is odd and the number of ones is even, right? So exactly the same logic. So you see that already, in one slide, you're already moving further. Okay, and this is the joy of combinatorials. Right? Okay. Now, consider the case of two heaps, where we have, it's a special case, m counters and n counters. Now, suppose m equals n equals 4. Now, this is the point, right? Now, whatever move player 1 plays in one heap, player 2 can copy exactly that move in the other heap, right? 4-4, suppose you remove 2. I will respond with removing 2, so that it's 2-2. Is this clear? So, you can keep on doing this, and at some point it will come to 1-1, and then whatever you do, you take, right? So, it's clear that by using the copying strategy, when m equals n, you can show that it's losing for player 1. On the other hand, right, suppose m was greater than n. Now I know that if the sizes are equal, it's a losing position. So if they're unequal in size and it's my turn to move, what's my strategy? I just remove the larger number from one of them and present you with the equal size one, which I know is losing, right? So you will lose. So if the two heaps are equal, player 2 has a winning strategy, right? And if the two heaps are unequal, player 1 has a winning strategy. So the copy strategy is a very nice strategy to make. And so let's state it as a lemma. It says that for all mn greater than or equal to 0, mn is winning if and only if m is not equal to n. Okay. Now, if I have 3 or more heaps, analysis becomes difficult. I mean, already if supposing you look at 2, 3, 6, it's horrible. There are just too many choices. Right? But then that little lemma that we had, we can put to use. But for that, first let's look at a more general way of thinking about this. A representation helps at this point. Okay. Observe that every finite extensive form, don't worry about that. Every mean is actually of the form 0, or there are several, you have the choice of m subtrees. Right? I mean, it's a tree which has no nodes at all, or it has got a root node with m subgames, right? So the move I make is going to put it into one of the m subgames. So let me think of it as 0 to represent the root node, and that choice into these m subgames as g1 plus g2 plus gm, where they are all the subgames. So 0 we can think of as the empty game because no player can make it. Now, this business of using numbers and talking about games as numbers is something that Conway taught us. There is a lot more to this. We'll get to it. But this is the fundamental insight. This little idea already, takes us quite far, as we see. Now, choosing between subgames has a very interesting algebraic structure. Suppose you have a game which has m subgames, and H which has another n subgames. Now I can define an addition operation on the two games as follows. Well, I build a new game where I make a choice to go into game G or game H. I'm going to play both the games, right? So what does it mean? Either I go into the left game, right? In which case I'm going into one of G1 or G2 or Gm and keeping H alive, or I'm going into the H game, in which case I'm going into one of the subgames H1 to Hn and keeping G alive. So that comes out as G plus H. Now, when you write it out, become G1 plus H plus dot 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 Gm plus H plus G plus H1 to G plus Hn. This is a very interesting sum operation. This suggests that the notation 136 for that game, I might as well write it as 1 plus 3 plus 6. Just notation, right? And another notation that I will use is to say G is a subgame of H, I'll say G is less than or equal to H. Okay? Because, well, these are things that we are familiar with. We are familiar with using addition, using numbers, using ordering. So let's just see if that helps. And it does. Now, once we have game expressions, that we are writing this plus this, etc., a natural question that arises is when do we consider two games G and G prime to be equal? I want to write equations on these and solve them. That's what we usually do, right? Okay. It's only for, okay. I'm not going to say anything about more general games. Sorry. So the definition is this. G1 is equivalent to G2 if and only if, whenever I take a game H, G1 plus H is winning if and only if G2 plus H is winning. Or equivalent way of saying is that G1 plus H is losing if and only if. So basically, two games are equivalent if whenever I place it in context, right? We are used to congruences in algebra, right? I mean, how you think about it. Whenever I place it in the context of any game at all, the winning or losing behavior doesn't change. Why this particular thing? Well, you really have to spend time thinking of many definitions and so on, and finally you will see that this is in fact the right definition. Another thing that Wilson talked about with Conway, right? He would spend lots and lots of time with definitions, playing around with norms. Now, you can check that this is indeed a Williams relation, it better be after all. And you can check that 0 is indeed the 0 of this particular addition. About that G plus 0 is the same as G. Now, therefore, we said for all H, right? Therefore, G1 is equivalent to G2. Then G1 is winning if and only if G2 is winning. Converse is not true. And all losing games are in fact equivalent to 0. And this is something that we can do. This is the loser's lemma. It says G is losing, then G is actually equivalent to 0. Now fix a losing game G. Remember your 1-1 that you have presented. That's a losing game. Or MM. Now I want to prove that for all H, G plus H is losing if and only if H is losing. Right? That's the idea. Yeah? Now we prove by induction on H that whenever H is losing, so is if you take a losing game and add something to it, it remains a losing game. Assuming this, the other direction is true. So we can skip that. Now, suppose H is winning, right? Instead. Then there is a move to H prime that is losing, right? We know that. And by claim above, G plus H prime is losing, right? Now, there is a winning move in G plus H because there is one which takes you to a losing, and therefore G plus H is winning. So, very simple argument that tells you. Now, I need still to prove this particular induction. Okay, let me skip this. I don't think we're going to get very far with this right now. I assure you that it's a 15-minute working out of things carefully by subtree induction, and get your induction hypothesis right, and you can see this. But the benefit is enormous. So what is it that we have got? We have got that if H is a losing game, then for all G, G plus H equals G. This means that every losing subgame can be ignored. And that's the beauty of it. Right? If you have a losing subgame that is there, I mean, intuitively it makes sense, right? I am at a node in a game, and I know that there is a subtree that is losing, right? Who cares? Going into that subgame is of no interest to me at all. Right? I might as well ignore that. That's exactly the intuition that a player uses, which you can prove by this lemma. Now let's use this knowledge to analyze a sum like 1 plus 2 plus 3 plus 4 plus 5. Right? We have no idea how to solve this game, right? Now consider 1 plus 2 plus 3 as a subgame, right? Now in this, removing an entire heap leads to a winning position, right? Because we know that in two heaps, when the number is unequal, you know that it's winning, right? So reducing any heap leads to two equal heaps, which is losing and winning. So there's no point in reducing any heap at all, right? Whereas uh, removing an entire heap leads to a winning position, and therefore this position 1 plus 2 plus 3 is in fact a losing position, right? Is this clear? Yeah. So there, now we have got a subgame which is losing, and we can ignore it, right? We know that 4 plus 5 is winning. We already seen two heap game where the number is unequal is a winning position. So 4 plus 5 is a winning position. 1 plus 2 plus 3 is a losing position, which we can ignore. Therefore, we know that 1 plus 2 plus 3 plus 4 plus 5 is winning. Right? Suddenly, we are in business. We can look at much longer points. Okay. Can we get some more general mileage than analyzing simple mean heaps? Can we get beyond? I mean, what about 183, 674, etc.? Right? How fast can we get there? Now, there is a strategy that works for this, and for that you have to answer the question. Now, how do I ensure that I don't lose a chess game against a grandmaster? Do you have any strategy for that, Amrika? No? Okay. I mean, uh, you want to play a game against Larson, right? I hope you do. And you want some strategy to make sure that you play well. Right? At least you know, try for a draw. Okay. So there is a, again, childishly simple idea. Okay. So what I do is I have to play against Larson, and I have no idea how to play against Larson. Right? So what I do is I challenge Vishnath and Anand to a game. Okay. And I play two games simultaneously. So one game I'm playing with Anand, and the other game I'm playing with Larson. So let's say Larson makes the first move. He plays white. Now I have to respond as black, right? Now I play white in the game against Anand. What is the move that I play? The move that Larson made. So I play that move. Now Anand is going to respond with something at the other, black. It's okay, what do I care? I play that black piece move to Larson. Now Larson must respond with something on white, which I play to Anand. So basically, Anand and Larson are killing each other. I am merely the one who's. So this is called the copycat strategy. The copycat strategy is using a strategy from one game and using it in another. Now, that's a very interesting strategy that you can, when you play games concurrently, that you can employ. And that's exactly what is needed to simplify the analysis of NIM. Now, it's an important principle in bipartisan games. It's actually what this kind of copycat strategy works beautifully in almost any bipartisan game. Bipartisan means that both players have the same set of choices. And the lemma is very simple. It says G plus G is 0. Right? That is, here is an addition where, you know, uh, not worry about that. So what does it mean? You take any game G, right? Assume that the claim holds for all subgames, right? A G prime less than, I should say. Now, what does a move in G plus G look like? Right? It will take you to some subgame, right? Any move which will take you to G prime plus G, because in one of them you will make a move, or G plus G prime, which is the same. It's commutative. So now we know that this is winning, right? Because G prime plus G prime is losing by induction hypothesis, right? Why? Because in G prime plus G, you can always copy the move that you took to G prime, right? That move I can copy in the other game, which is also of the form G. Therefore, I can reduce it to G prime and present you with a losing position. Therefore, that G prime plus G is actually a winning. So if G prime plus G is a winning position, the original game G plus G must be a losing position. And we know that all losing games are equivalent to 0, and therefore G plus G is 0. This is it. And so basically, the class of games with addition forms an abelian group. And it has commutativity and associativity are very easy to see. And 0 is the neutral element. Uh, and we have seen also that every element has an inverse, and in fact, it has its own inverse. Right. Now, the beautiful algebraic structure here, uh, I hope it's reminiscent of some very familiar algebraic structure that pretty much everybody knows. Now, let me actually now I hope you can see that once you've got this, you can simplify the analysis of pretty much any NIM heap that you're given. So the NIM game can be completely solved. You can use algebraic machinery to bring it out irreducibles and solve the problem completely. It's a very nice algebraic structure involved. And all I'm saying is that that works for all bipartisan. And that what we have seen is a glimpse of the great theory, as it's called in games. And Conway took this much, much farther. And this is this beautiful book by Conway called Games and Numbers. And so what he shows that there is a distinguished subgroup of games called numbers, which can be also be multiplied. That's a much more complicated operation, so I don't want to take it up. And actually, so what you get is a field. Okay. So you get not only addition, you also get multiplication, and you get a field. And this field contains both the real numbers and the ordinal numbers. And in fact, Conway's definition generalizes both Dedekind cuts and von Neumann ordinals. And so in this little book called Games and Numbers, he builds an entire universe. It's a beautiful microcosmos of numbers and games, which are, so what are called numbers here are games here, equivalence classes of games, which are called numbers. And in that, he can do the entire von Neumann ordinal construction. And it's got, numbers which are infinitesimally close to 0 and ones which are infinitely large, lots of them. And in fact, Donald Knuth wrote a novel called Surreal Numbers. He calls them surreal because in Conway's numbers, every real number is surrounded by a whole lot of new numbers that in fact are closer to it than any other actual real number is. Right? So the construction is absolutely phenomenal. And well, again, I remember when I was in New York, I saw this slim book in the library long before I met Conway, at least 10 years ago. And I saw this book called Games and Numbers and absolutely fell in love with it. And I remember, in fact, running around and trying to get it photocopied so that I could take it to. And then I found it was there in TIFR library. So later on. And it's a beautiful construction and one of the, I must say, brilliant pieces of work that Conway did on foundations of mathematics, which he didn't build on later on, but there is an entire number system constructed from and he did it, purely for the joy of such a construction to show that it's possible. Now, can one do analysis on this particular universe? I don't know how you would do analytic calculations or that. But the point is that it's a very rich structure. Knuth's novel is also something of a pleasure to read. I would strongly recommend. Okay. Um, Other things that Conway did, just a quick breeze through of many things. The beautiful problem that Conway worked on in 1960s was a sphere packing. The question is, I take a region of the Euclidean plane and I want to fit as many circles as possible. How would you go about it? Um, well, ideas. It turns out that the best way is to divide the plane into one big hexagonal grid and circumscribe the largest possible circle inside each uh, hexagon. And this gives you the hexagonal lattice. Now you can generalize this to spheres, and that is the sphere packing problem in 3 dimensions. Now, Leach in the 1960s defined a lattice which he showed was the most efficient packing of 24-dimensional spheres in 24-dimensional space, right? Rather than circles in 2-dimensional space or spheres in 3D space, it's working with 24 dimensions. How do you even think about 24 dimensions, right? But what Conway did was to work on the symmetry group of the Leach lattice, and he came up with what is called the Conway group now. And in Conway's writings and interviews, you should see his sense of wonder at that group. He said, this is something remarkably beautiful because this kind of symmetry I've never seen. So for him, it was that the aesthetic element which was the most exciting thing. And he says, my life changed completely. And he said, how do you even envision something in 24-dimensional space? And so maybe I could give a link to that interview as well. The sheer wonder of. Uh, I think this was talked about by Professor Robert Wilson last week, and this is the monster group. In 1979, Conway and Norton conjectured on the relationship between the properties of the so-called monster group and the J function. Now, it's a collection of symmetries that appear in you know, what, how many dimensional space? Some deadly number. Right? And the paper was called Monstrous Moonshine. And later, Borchard's, I typed it. He got the Fields Medal in 1998 for 2 weeks. Uh, this is what Professor Wilson talked about. Knot theory, Conway's contribution to knot theory. Every knot you can think of as closed loops of string. The fundamental problem in knot theory is, if I take a knot, can I apply finitely many allowed operations to go from one knot to another? And that's when you call it equivalent. Now, mathematicians have come up with many tests which you apply on a pair of knots, and if it leads to different knots, basically some kind of invariances that you study to check whether they are equivalent or not. Alexander polynomials give you an efficient procedure but not unique. And Conway came up with efficient and unique way of doing, and these are called Conway polynomials. The whole theory around this. And Conway also gave an arrangement of knots which makes it easier to study. I don't even know enough about these things to explain, but I just, as I said, toured through many different areas. Last week, Professor Wilson was talking about quantum mechanics and the free will theorem, an amazing piece of work, again, that Conway was involved in. So Conway contributed to many areas of mathematics. Theory of finite groups, classification of finite groups. That's the big tome that we heard a lot about. Number theory, combinatorial game theory, as I mentioned. He was one of the founders of combinatorial game theory. Coding theory, geometry topology, algebra, analysis, graph theory, algorithms, and then quantum mechanics. And last but not least, cellular automata. Right? I mean, game of life, which led to. So, uh, surprising range of contributions in one lifetime for any mathematician to contribute to this wide, such a repertoire is something that's phenomenal for us to. One thing that I want to end with, and Conway was known for his obsession for reducing proofs to simplest terms. Again, Professor Robert Wilson took us through that, and this, you know, uncompromising insistence on simplicity. And one paper that I like a lot appeared in the Intelligence set by Karamzadeh in 2014, where he tries to argue that Conway's proof of Morley's theorem is in fact the simplest possible proof. I mean, how do you prove that it's the simplest possible proof? Right. So he actually undertakes this task that there could not be a simpler proof of Morley's theorem, which I found amusing, but also very interesting. And Conway and Shipman wrote in the Intelligencer a very beautiful article called Extreme Proofs. So they look at the kind of values that you can associate to proofs. You know, they talk about brevity, generality, constructiveness, visuality, or non-visuality, surprise, elementarity, and so on. They actually give 7 proofs of the irrationality of I strongly encourage everybody to read this amazing paper. We all learn that square root of 2 is irrational, right? And there is one proof that pretty much every child in school can repeat. Uh, and supposing it is rational, it is of the form p by q with no common divisors, and then yeah, you go through this whole exercise that supposes it's rational and go over p squared, q squared. It's, this whole fun stuff out there. Right? But how are there other ways of proving it? And then when you start thinking about it, there are actually really interesting proofs, and they want to look at what are the simplest proofs possible, and in the sense that they use the least number of axioms or the least axiomatic machinery, and that's an amazing exercise. Uh, I'll quote from that uh, paper that they say, indeed, because at any given time there are only finitely many known proofs, we may think of them as lying in a polyhedron, and the values of functions as linear functionals as an optimization theory, so that any value function must be maximized at some vertex. We shall call the proofs at the vertices of this polygon the extreme proofs. So actually they define it, they attach values, and which are linear functionals, and give you some way of measuring proofs in some sense. And so exactly like we talked about maxima, you can explore the vertices of the polygon to find the extreme proofs. Okay, let me end with a quote from Siobhan Roberts. I don't know if I'm pronouncing Conway's biographer. It's a beautiful biography. Again, I would recommend to everyone to read Conway, where she, and in an interview where both of them are present, and she says, John bills himself at once as a know-it-all. He wants to know absolutely everything. That's his goal in life. And a professional non-understander. I love that term. Since on most subjects he starts from a place of not knowing. But the nature of his pursuit is very meandering, following one tangent after another in his playfully circuitous way. So this playful approach seems to be very, very characteristic of almost everything is doing. Playing with notions, playing with ideas, take where, let it lead you to wherever it wants to go. Thank you. I should stop sharing.
Thank you, Jam, for the nice talk. So yeah, we had a couple of questions to ask you. One was from from free will theorem itself, but it seems that you are not going into explanation of free will theorem.
Sorry, once more. I missed the. I wasn't able to understand. Yeah.
Yeah, and like we had a couple of questions to ask you. One was
Yeah.
from free will theorem and its implications, but
Well.
it seems in your presentation you skipped that part.
Oh, I thought Wilson was talking about that, right? I mean, and he's the expert. I don't
Yeah,
know
but
enough quantum mechanics to even attempt to. I mean, it's just an informal statement of that I was using, but uh, I mean, yeah, it, it basically says that if you could fix all coordinates, positions right now, you would still not be able to predict the movement of a particle. Right? That is the new statement that I quoted there, which you know, and which is what Conway in the interview calls free will of the particle. He says if a theoretical physicist can have free will, why not the particle? As a joke. But uh, yeah, I don't know enough to go into what I try to read it.
When you met Conway for the first time, you say that you didn't know him, like you didn't know his face. So you are
Yeah,
when
yeah.
he
And
he approached him.
yeah, I mean, I had never seen a picture of him or anything like that. And also, I think at that time, well, 90s, yeah, he was very famous, but I didn't know. I mean, uh, for me, the introduction was from the book Games and Numbers. And after that, that was, I almost fell in love with it. That was in the 80s for me as a student. And then I had seen something of, I'd heard of some comedies, but not very much. Yeah, one moment, I'll just put on the light. So yeah, some bearded bloke who gave me a lift. But yeah.
Okay, how he was at like when you went with him for the car ride? How he was like? He was. He
Yeah, I mean
doesn't seem in the interview that he is very like a very sophisticated person. But although his works are very sophisticated, but was he very
yeah,
sophisticated as a
as I said,
person?
I mean, here was someone whom he had never seen, and he was giving a ride, right, car ride, and all that. He said, "What do you do?" And I started telling, and I mean, basically, it started with asking, "Where are you going there?" And I was talking about the workshop I was going to. He wanted to know what it was about, and I was telling him about these things. And the moment he heard, "Oh, theoretical computer science," and he said, "Oh, you should be interested in problems in combinatorics and graph theory." And then he said, "Okay." And yeah, it was just problems after that, right? Discussion problems, and that's I think. Like he loved posing and discussing problems, like I said, with school children to anybody who was interested in problems. And that's reputation he had, and then I saw that too.
Jam, you in your article, you have used this term mathematical artist, right?
Yeah.
He said he has been using this term for a quite long time. So why you call Conway as a mathematical artist?
Actually, that's from one of Conway's own interviews. I think when the book came out, uh, the New York Times had an interview with him, and I think that's the one where, I mean, he doesn't call himself a mathematician. It's just, but then, he tries to argue that he would think of mathematics as an art, much more as an art than a science, and he likes to. I mean, he basically, not only in that and another interview as well, he suggests that doing mathematics is like doing art, and so he firmly believed that a mathematician is an artist of some kind, and that comes through in so much of his work. So, and aesthetics is very, very important for him, and symmetry is very important, and the constructions are very, very elegant, and the striving after simplicity. So there is so much of an artist in him, and and
This makes me very happy, really. Sorry, Ramanujam,
oh
you
yeah,
have a
yeah,
thing?
please,
Okay.
yeah.
Actually, I would like to see this interview, read this interview.
I
If some of you can send it to me,
Yeah,
uh,
I will do that. I will do that.
yeah, because I wanted, you remember I asked Professor Wilson about Conway's philosophical position in regarding, and he really didn't answer. And but what you said he definitely, though perhaps not that explicitly, but definitely he had some uh, philosophy of about
Okay,
mathematics,
so
doing
on
math.
that, on the philosophy, in the philosophical front, right? In fact, I now have to find out exactly where, because I have read, you know, see, it's. I am told that Conway described himself as a philosophical mathematician somewhere, but I've never been able to find precisely where he said that. So if somebody finds the original quote, I'd be happy. But when in fact the interviewer says, you describe yourself as a philosophical mathematician, what do you think of this? So this is how the whole thing starts. But I've never actually found the source where Conway said, calls himself a philosophical mathematician. And so but one thing is clear. I mean, I think you're also last week somebody was asking about uh, the course that Conway taught on foundations of mathematics.
Uh,
And
Myself,
I
I
in
see.
fact read by one of other mathematicians from Cambridge. When Conway passed away, there were these tributes that Princeton organized, where I've now forgotten the name. It will come to me later, or I'll find it. Who says that? Oh yes, I attended the course, and but it was basically forcing. I mean, the
Okay.
main, Conway. Remember, this was late '60s, and
Mm.
Cohen's forcing had come out, and mathematicians were very much interested in that. And basically, Conway wanted to teach forcing, and
Oh,
so there is another one whom he met years later, and he said, "Oh, I attended your Foundations of Mathematics course." And Conway said, "Oh, I'm glad you survived it," because apparently it was a killer of a course. Because Conway used the opportunity, used the students as a way of trying to understand forcing, and so that is what the course was about. So, but I told you about games and numbers, right? I mean, it's if that is not foundations of mathematics, what is, right? I mean, he actually develops the entire system, and as I said, he generalizes Dedekind cuts and ordinal construction. So he does all that. No, but for him, foundations was again mathematical in that sense. I mean, you don't philosophizing about it should be again in mathematical terms. I think that is the spirit that comes across. But beyond that, he doesn't discuss it further in interviews that I read.
all right. Thanks. Mamalika, if you can find these interviews and
Yeah, I will
papers,
send the link. I
okay,
will certainly send
that's
it to you.
fine. That's fine. Yeah. Okay.
At least a couple of
Please,
ones I
No, actually, we can perhaps derive some philosophy out of his
possibly.
activity,
Yeah,
and not perhaps explicitly he didn't say anything, but
yeah,
uh, doing numbers in that way.
yeah,
I mean, as you presented also,
yeah,
if somebody can derive that, okay, he was playing with it with numbers, so not the usual way, um, a very unusual way of playing with the numbers. So that makes
yeah,
uh, that gives someone somebody can derive something. Actually, I got to know Conway really from, I mean, from the writing of some of these philosophical writings uh, by somebody else who was writing about the foundations of mathematics and interpreting number in a different way and so on. No.
right, right.
So
Yeah,
yeah.
yeah. But
please.
art is something that he does talk about at length. That
Sorry.
doing mathematics is art to him. That he talks
Yeah,
about.
that I actually also my understanding or my belief, and of course, definitely it is a different kind of art. But when it is an art, it doesn't have necessary connection with truth. Uh, that is the main issue connected with the foundations or philosophy. See. Okay. Okay.
Please, sir, if you want to comment anything else,
No, I have already
don't mind.
commented. Yeah, I have already commented. I have already entered this scenario.
Sir, you were talking about like reading from about Conway from someone else writings on philosophy. What was that? Can you please like can you give a
I
line?
don't exactly remember, but it was connected with the philosophy of mathematics. Uh, those who do not were anti-realists that way. In the philosophical position, they want to have some uh, detach mathematics generally from sort of usual facts. That means the mathematical statements being true and false make something um, different from truth and falsehood of other kind of statements. Uh, for instance, if somebody says that angle sum of a triangle is a true right angle, is true right angles, what is the meaning of the truth of this statement? Uh, so, uh, so I most probably I read uh, about Conway through some such writings where the author mentioned that Conway gave interpretation, game theoretic interpretation to numbers, which, as I see, also I mean, got from Ramanujam's talk, partly at least. So that is how I got to know about Conway first time.
Okay, sir. Okay, thank you. So now I want participants to ask some questions.
Anybody has?
But I have a proposal.
Yes, sir. Sure.
Can you bring out actually after all this one month's exercise in talks, etc.? Can you bring out a small thing at least on Conway? I mean, you can collect, not necessarily the talks given here, but maybe other talks. So Ramanujam's already, I mean, what he has already written. So just collating them together and just making it them available. That will perhaps be a good. What do you think, Ramanujam? Will that make sense?
Um,
There are
well,
lots of
already
things already.
the collection of talks is already a tremendous resource. So if there is some written form, it's even better. But yeah,
Shukanto sir, I want you to comment on this.
No, the proposal is good, but as Jam has said that lots of resources are there, but uh, in our it's 1 month effort, we are getting so many talks, so many information. So we can collect them, we can write them and we can enrich them and get a collection. You can prepare some collection. What that's right.
sure.
So in that case, we will be getting back to the speakers and again troubling them with asking for writers. So
Yeah,
that, yeah,
right.
please bear with us in that case.
We can do that one.
I think you can simply just put the slides if they want. Just put the slides
Yeah, that's
together.
why I said that's already there as a resource. So
Yeah,
Just
right.
put them together and make in one. So
So we are thinking about that. We are thinking about that. So if you can collect, if you can write down all the information, all the speeches, then maybe we can prepare a good resource. That may be a good resource to us.
no, in
We are
fact, you see, in
thinking
the
on the
slides you will not get the story that Ramanujam told. He
right,
was
right. Of course.
standing in the
So
field.
slides will work only.
I know Shovik had some questions. Why
yeah,
it's
So we
Uh,
yeah.
yeah. Hi. Hi,
Hi,
John.
Siobhan.
Sovik here.
Yeah,
Yeah.
yeah,
So my first question is that Conway love to attend the um, math camps
yeah.
with some
Children.
school childrens and 12 to 13 years one math camp in every year, and another with 17 to 19 years.
Yeah,
And as far I know, you also very much interested working with school childrens about mathematics.
yeah.
So I'm very much my first I want to know your comment, the impact of uh, organizing math camp for school children's in a mathematician's life. Uh, what's the impact of organizing such kind of math camps? The impact of this in a life of a mathematician, how the thinking process of a mathematician. If you share your personal experience about it, uh, this is my first question. That after, because the length of this answer of this question may be random, so after this I will ask the second question.
Okay. Yeah. Yeah. Sure. So the thing is that I mean I think that kind of interaction is tremendously enriching. I mean that's one reason for me. It has always been an enrichment. I can only talk about my personal experience over many years now. Uh, I've been interacting with school children at different age groups in this kind of well, math camps, science camps, these kind of fairs, exhibitions, what have you. And because children bring to projects a certain freshness, a certain approach, which we forget, which we all have in us, but we forget because we are trained in in particular ways, and it's very hard for us to think about problems ab initio, right? Uh, Problems like bare hands approach, as I mentioned, right? It's very hard to actually do that because you are trained in a particular way, and especially like I work in a particular area. I'm very comfortable with logic and automata theory, and I tend to see automata or some logical machinery in all problems I see, right? That's natural. But then uh, what happens to all that bit of number theory that I learned, or this I learned, or that I learned? It's all there somewhere, right? Now when you start doing geometry with children, when you start doing algebra or number theory or any of these things with children, coding theory, I remember doing any of these, it opens up pathways that are completely new. I'm not saying that it immediately gives you new research problems that you start solving tomorrow, right? That may not happen. But I mean, you do very quickly come across problems that are very hard, very difficult. And the kind of insights that are needed to solve the problem, yeah, that I mean, my favorite example that I like to take is in one of those things. Suddenly, one class 9 child posed a problem to me. He found it in some Russian problem book and asked me, um, show that 5,555 raised to 2,222 plus 2,222 raised to 5,555 is divisible by 7. Now, this is what I mean, right? When you do, uh, now this is not a hard problem. It's not a difficult problem, but no, it's a difficult problem. It's not a hard problem. Um, when you look at a problem like that, how do you approach a problem? You know, of course, you realize that the actual numbers are completely meaningless, right? Nobody expects you to compute the number, add this, and find out that it's divisible by 7, right? So you have to use some general principles. So what is the form that you're going to use at that point? First try is a to the b plus b to the a. Well, that doesn't take you very far, but you start looking at a to the n plus b to the n, then there are some all sorts of things start popping into your head. Now, I'm saying that these are what those children are going through as well, right? I mean, somebody who's trying to solve this problem also is trying various things. Now, what are the things that you try? This is what I meant. This is what I mean. Working on problems like these that actually children work on frees your mind in ways that is phenomenal. Right? That it makes you receptive to lots of ideas. It makes you receptive to many techniques, and this after all, in almost all mathematical work, finally you are always grappling with this thing between form and content, right? Looking at form and content, and there, uh, looking at many different forms. I think that's precisely where working with children helps. I don't know if that's a good answer, but I would say, and I have no idea for Conway. Like I said, Conway was very much interested in posing puzzles, creating puzzles, solving them, and asking children to pose puzzles to him. So I have no idea how he felt during that and how what impact it had on his life. But clearly, he enjoyed it immensely, and that's very, very clear.
So, my actual, okay, Mr. want to say something, I think.
Yeah.
So,
No, you continue.
Sorry.
Should we
uh,
continue?
So my second, not second question, the continuous one, actually. The so what do you think about the computational ability in terms of computation, the thought process of children? Uh, uh, I want to know basically your comment on the computational point of view about this particular thing, because I think when we think uh, uh, about any problems, suppose if we start working a small problem, so we somehow think in a centralized manner, like the Turing machine or something, the stored architecture, stored instruction set, some instructions are stored, and we will try to do uh, the computation from that stored instruction. So is there any possibility of uh, any other computational model or any other computational point of view to explore the process the children's try to solve the mathematical problems? This is the first one, and obviously the second point is that if you consider game of life or cellular automata, uh, this is something, there is no centralized control. So when human try to solve a problem, uh, suppose children try to solve a problem, so is there any decentralized uh, point of computation going on, or that kind of things happens? So specifically, I want to know your comment on that.
Um, I think that's an extremely difficult question to answer because, I mean, I think analyzing how the strategies used by children is something that we know very little about. Uh, I mean, anecdotally, experientially, we say many things, but in terms of doing science with it, to actually understand the space of strategies and how they are navigated, we know very little. So, by the way, I mean, in general, when it comes to game theory, the understanding the strategy spaces is something that we have for only a very, very small, you know, class of combinatorial games. In general, game theory is very, most of game theory will only talk about existence of optimal strategy. What you are talking about is actually composing those strategies on the fly, right? To come up with. We know very little about that. I mean, in fact, we know very little about the mathematics of that. Uh, that's one comment. When it comes to real human beings and how they do, I'm afraid we know very little about it. Even with all the advances in neuroscience that I hear about, there are people who are doing some experiments. I think, but I must say that it's quite primitive. We don't have anything sophisticated enough to talk about like the kind of computational model that you're looking for. We can hypothesize some, but but on decentralized control, I mean, even if you start with Turing machines, right? Even if we start, if you break up the cells of the Turing machine, right, to just autonomous entities and link them up. I mean, there is a theorem you can prove that the what you can compute is exactly the Turing machine. Right? I mean, the Turing machine is so robust that in terms of computational power, it's not going to change very much. And that's part of the learning that we have had in the last 70, 80 years, right? I mean, you can do pretty much what you want with the Turing machine model. It's just that it might be better to have such forms of machines where, which, in terms of computational power, may not change anything, but in the mechanism and the way they operate, they may give you insights that are, like cellular automata give you insights which are profound. The circuit model of computation, equivalent to Turing machine, gives you very different kind of insights. It depends on what you want to prove. I mean, I would say if we could get hold of, if you're talking about navigating strategy spaces as the main thing that you are after, right? And what kind of computational model is appropriate for it? I don't have a, I don't have any answer to this, nor have I seen any answer to this in the literature. But I understand that something which has tremendous parallelism matters. But the way you compose things, I mean, basically those are algebraic structures where those composition, those operators, we understand very little. Strategy composition is something that we understand very little. That's really the heart of the matter. Yeah. So
I have some question and comment on this. Actually, what you are saying that Conway was interested working with students in that in that sense that he arranged the math camps. So the point is what Shovik was asking, uh, as I've understood his point, that the children, so school children, say KG students, children of say primary section. So they learn some mathematics like addition, subtraction. Then they learn say GCD. So they have some learning process. And what they do sometimes, what we observe, I mean, probably Jam, you have organized so many things, so many camps, and you worked with even school children, primary school children. Probably you have some experience. No, they have some some kind of computational ability. So they understand, they learn math addition or subtraction in some special way, and they apply that knowledge to find some other things. So like when they learn GCD, they use the previous knowledge of division, multiplication, addition, etc. In this way, step by step, they learn. Now, when we call, say, when we, if somebody asks me to find some GCD or LCM of few numbers, then what we do, we just recall that procedure. So as if some,
okay.
some function is stored in my
I,
mind.
I know, understand what you're saying. I was talking about the problem solving strategies that children use. And I was saying that space of strategies that children employ for solving problems, right? That's something that is, very difficult and unexplored. What about the computational algorithms that children employ? Right? Now, again, uh, mostly one major I did a lot of work on what we called folk mathematics, right? Mathematics that people out there, people use. And I mean, because you can go, we know that farmers look at the field and estimate, like right now, for instance, in March or April in India, it's very common to take leases of mango orchards, right, groves. Before the mangoes start fruiting, you actually take the leaves and you quote some money. How do you quote that? Because you look at it and make an estimate of how many mangoes you are likely to get. You look at the flowers, the flowering tree, and you make a guess. You use an algorithm because it's money. After all, you don't take, you don't quote random numbers because if you quote too much and get too few mangoes, you're going to make a loss, right? And if you quote too low, you won't get the leads. So you have to quote optimally, and people follow algorithms for doing this. And so this is what you call folk mathematics that people employ, right? And when you go to a shop, for instance, you buy something for 62 rupees and you give a 100 rupee note. The person doesn't, shopkeeper doesn't subtract and give you the 38 rupees, right? It start giving you some money, say, okay, 70, then 10, then 20, and say 100. Right? Now, if you ask the person how much you gave, you don't know, but he knows that it's a correct algorithm. Right? So people follow many different algorithms. With children, it's a little complicated because what we do in school is to privilege a particular algorithm and make you forget all the other algorithms that you have in mind. Right? So in fact, the moment you go to school, I mean, if I ask somebody on the street what is 27 times 6, person may think of 20 times 5 is 100, okay, 20 times 6 is 120, like that. You might do something like that. But once you have gone to school, you realize that if it's 27 times 6, you must put this on top, write this on bottom, and then start following. So I'm afraid, in fact, the sad part is that the computational algorithms that you will find that children, as you said, from school, is become very limited because you are trained to, the tyranny of the textbook, and one algorithm that has been taught starts dominating. Of course, many children grow out of that. They think on their own. They come up with techniques, but that typically goes into what I call problem solving strategies and those. But
Hello.
new algorithms, I've seen some. I've seen a few, but computational algorithms of various kinds. Uh, well, yeah, I mean, I have not seen one which uses a lot of the decentralized control that Shavik was talking about. But there are many different patterns coming. Yes.
Next question comes. See, what you have said, the algorithm, what children do in school is one way, one thing, and the game of life, it's working principle is, as I've understood, is a bit different. So my question was, how the people like Conway, who work with children, who try to understand the thought process of children and the game of life, how they match. In case of game of life, traditional algorithms, don't work. Okay. So do you have any comment on this?
I don't know enough to comment on that. I think the thing is that, in some sense, you have to take a game for what it is, right? Your children. I mean, if you start doing a game with hidden agenda, or that it illustrates some point and so on, you're not going to get very far. It should be the game that's the playing the game should be interesting for its own sake, and the puzzle should be worthwhile solving for its own sake, and that's a golden principle, which is right because they're trained to smell these hidden agendas. Right? I mean, you come with all you come with hidden with these things. It's very easy to smell. So that only disturbs the original thinking process. But the point is that lots and lots of game playing. I mean, game playing is mathematical, and, because after all, game playing involves strategizing and coming up with strategies that apply in many different contexts. So that if you can articulate it inside your head and actually perform that, so games of strategy are different, and puzzles are also different. That's really the. I mean, I don't know what. I'm just saying that that's really the link, and the moment you actually start playing with ideas, playing with numbers, playing with formulas, playing with shapes and forms, like with geometry, the same thing starts taking over, and that to me is the reason. And some of them have the power to encapsulate a whole lot, like again. But yeah.
One last question, that is what General has asked. Jam, are you
Yeah, yeah,
going to
yeah.
answer it? Like,
Yeah. So yeah, thanks very much. Thanks for reminding me. So, yeah, combinatorial game theory start that way. What about undecidable problems? There are lots of undecidable problems. In fact, the fact that I said there is a group structure, right? So the NIM game is very very simple, but there are many games that they are very easy to set up. You can practically take up any of those two-player games that you see on mobiles, right? And or what are called one-player games, where you solve Tetris or some of these things that you can solve games on mobile phone that you see. Uh, Almost all of them you can try to do combinatorial analysis, and very often you will find that the word problem is undecidable. I mean, the word problem is what? If I take two game expressions and ask whether they are equal, right? And that's undecidable. And in fact, it's very easy to come up with uh, games where, if you look at the associated group structure, where the probability is. So, in fact, in many of those, the challenge is to come up with simple ones that you can solve. And of course, Conway was a genius in coming up with that kind of simplicity. I don't know where he got that from, but coming the rules very often uh, become very hard. So, yeah, and there is a project on internationally to classify these. You know, uh, you know, game like we talk about problems being complete for NP and complete for space complexity, you know, complexity classes. Games that are complete for different complexity classes. Correct. So you not only have, at the level of computability and incomputability, but all the way down the Gregor-Check arrow, all of them have complete problems. We are very far from that, but there is work on, and it's very interesting. Now you had
Okay,
something more
thank
to say.
you. Thank you.
Okay, so yeah, I have made you talk for like 1.5 hours
Uh,
already.
I have one small question. Uh, can I ask?
Yeah,
Because it's
definitely.
over, going over time. My question is for Jam and for also me, sir. Also, my question is about free will theorem, and I think when in fact few days back I have read this free will theorem for first time, and I want to know your comment on this free will theorem. In fact, philosophical comment on this free will theorem, because when you see everything in our surrounding, so the questions always attract us that who have created all these things surrounded by us, nature and all this. So, well, can you say something about your philosophical comment on this field theorem? Uh, Maybe my question is not too much complete, but I hope you can understand.
No, I understand the question, but I don't know what answer one can give because, um, see, well, it's a mathematical statement. It's a theorem, and it is about unpredictability of a certain dynamics, right? That's what they are talking about. They're talking about, hey, in the quantum mechanical world. But what they are saying is that if you supply the description to whatever precision you can think of, from this description, if I want to compute certain future behavior, there will be uncertainty. Now, you can interpret that as free will, etc., etc. But when we do that, we are anthropomorphizing. Right? I mean, we are a lot of the philosophical considerations that come from human thought and human action to action at the level of particles and at the level of. So I would have some worry about that, about what is lost in translation. Uh, that's the big one. Otherwise, uh, it's very liberating. Look at it asserts free will. It's wonderful. But what is free will at the level of human societies and human action, and where there is politics embedded in what we do? Whether that can be translated to quantum mechanical, I don't see that.
Lisa, you want to comment anything?
I don't know the statement of the theorem. What is the theorem? Ramanujam has said something, but what is the exact statement of the theorem?
No, exact statement will take a lot of time.
Stop it.
You should re-invite Wilson for it.
Ah, yeah. But can you,
What I wrote was an informal
because
paraphrasing.
without context, it becomes very difficult
Yeah,
because
it is. It is. And
I think we should not elongate anything to any extent that way. Context is very important. I mean, under what context this particular statement is made. And mm, so mm, my own belief is that you cannot say something which can be universally applicable, including perhaps this one also. So, okay, I don't know, Shobik, about this statement itself. I've never read it, but I can guess what you have said, and I uh, agree with Ramanujam uh, about. Okay, I will rather say that one should not extend everything too much. For example, the same thing happens with Girdles and Completeness theorem and so on. So, if you go, my own book's name is Ajampurna's Tattva, and the title itself I gave because of, I mean, it catches crowd. Sampurna Tattva, because people have their own uh, interpretations. They have all their incompetence in their minds, and they want to see some answer to their own incompletenesses in this book. So that was why I gave this name. But at the same time, it is true that in this book, I really wanted to make precise um, its applicability also. Uh, but at the same time, it is also true that some theories have sometimes surpassed its own boundary, and then you cannot really check it. For example, theory of relativity, it is one similar thing. Mm. So about this theorem also, uh, there will be many interpretations and misinterpretations. That is quite expected. Yeah.
Okay. Thank you, Mr. Thank you, Jan, for the nice talk. So
Thank you.
maybe I have already extended this. I told you that you have to give only 30-minute lecture, but I made it almost 2 hours. So sorry for that. And thank you for bearing with us. And so maybe I can move to the next talk.